Hello, my name is Minjae. Today I'll present paper named Graph-Based 3D Collision Distance Estimation Network with Probabilistic Graph Rewiring. Minimum distance is the distance between nearest points of two geometries. Acquiring accurate minimum distance is an important problem for safe and efficient robot manipulation, especially for elaborate tasks such as hanging objects. Compared to geometry-based approaches, data-driven approaches have parallelizability and the auto-differentiation capability. We categorized existing methods in twofold. One representative approach is utilizing point-based representation. However, due to the innate limitation of its representation, these approaches mostly suffer from low accuracy. On the other hand, graph-based approaches exploit graph structure. Especially they utilize edge features which contain relative coordinates. This fertilizes distance-related information because relative coordinates are closely related to Euclidean distance. Graph-based approaches can achieve higher accuracy with fewer points. Among graph-based approaches, GraphDisNet connects 1 to n inter-edges for message passing. However, as we extend this approach to a 3D environment, the number of inter-edges increases significantly. This causes higher message passing costs, limiting its application to 3D geometries. Therefore, we introduced the 3D graph-based collision distance estimator, GDNR, which probabilistically rewires inter-edges. From the node-wise score value Ri, we utilize Gumbel top K relaxation to select the top K nodes and connect them to each other. Here we also utilize a temperature parameter that can regulate the amount of randomness. This randomness prevents the selection process from falling into local optima. From this, GDNR has a more efficient wiring strategy than other baselines. Furthermore, exhaustive connections cause degradation in embedding, which means that as it passes the same message to the counterpart nodes, the embedding tends to be indistinguishable after message passing. In contrast, a selective strategy creates K-to-K connections. From these connections, message passing conveys embedding to particular nodes only. This enables the message passing process to achieve advantageous embedding. We also update the score value based on this embedding. Because the rewiring process is performed with the updated score, advantageous embedding helps the rewiring process so that informative connections can be created. Informative connections can carry local features which are more closely related to the minimum distance. Once again, this informative connection helps selective messages to pass and therefore creates advantageous embedding. From this iterative loop, GDNR can generate more informative embeddings than other baselines. GDNR has 3 stages. First, we construct the initial graph. In this work, we use triangle mesh of objects. We add randomly selected nodes as inter-edges for the information passage. Second stage is message passing with probabilistic rewiring. From the first stage, we get the graph structure and node feature, and feed these into MPNN and the probabilistic graph rewiring module. We first estimate the initial score value. For differentiability, we edit Gumbel noise and calculate perturbed score R. This score is used for node selection and the inter-edges is updated. The initial node feature is processed through one more MPNN with the rewired new graph for the node feature update. After L iteration, we process the final node feature to estimate the minimum distance. As an evaluation benchmark, we prepared a hanging task with 150 pairs of hook objects. For training, we created 2 types of datasets, a random configuration dataset and an RRT dataset, which corresponds to our hanging objective. The left shows the R-square and the MSE value of each method. We conducted our experiment in 2 scenarios: seen category and unseen category, which can prove the generalizability of each method. We can find that GDNR outperforms baselines in both scenarios. This empirically proves that our method can selectively connect essential nodes compared to other graph-based baselines. Further, we conducted a Bayesian study on the rewiring method. As the result shows, high randomness degrades the model performance, while no randomness case verifies that some amount benefits the model. Overall, GDNR achieves highest accuracy in both seen category and unseen category. Left side shows number of parameters needed for each method. GDNR requires least amount of parameters. Right side shows the inference time of each method. Among graph-based methods, GDNR shows the least amount of inference time. This proves GDNR's efficiency in time complexity perspective. To sum up, our model also operates efficiently with reduced number of required parameters and inference time while sustaining competitive accuracy. Next, we evaluated our method qualitatively. From RRT, we often acquire jerky trajectory. It can be transformed into smooth and feasible paths via trajectory optimization, which utilize the gradient from our method. This is the real-world experiment of hanging task trajectory, which is optimized with GDNR. We also tested our method for hanging trajectory with generalized hook-object pairs. Our method, GDNR, outperforms state-of-the-art baseline methods in terms of accuracy and generalization with efficient structure. Thank you.